We walk on it every day, right? The solid, unmoving ground beneath our feet. I mean, we think of it as the very definition of permanent. But what if I told you that was completely, totally wrong?
Yeah, it feels solid, firm, stable. The one thing you can always count on.
Nope, not even close. The truth is, it's constantly moving. It's part of this huge, slow motion dance that's been happening for billions of years. So that's the big question, isn't it? What on earth, literally, is powerful enough to move mountains and continents? To figure that out, we're going to have to peel back the layers of our planet and find the incredible engine that's churning deep, deep inside.
All right, so let's start our journey. We're going down right through the very structure of the Earth, from the surface all the way to the super hot center. Okay, first up, we've got the crust. This is where we live, our home turf. And honestly, it's super thin and brittle, kind of like the skin on an apple. And it's not all the same either. The crust under the oceans, way thinner than the thick continental crust that makes up, well, the continents. Now, go a little deeper and you hit the mantle. This thing is massive. A huge layer of hot rock that makes up most of our planet's volume. And this is where it gets really interesting. See, the upper part of the mantle, it isn't totally solid. It's more like a soft plasticky zone. And that crust we live on, it's basically floating on top of this gooey, slow-moving layer. Geologists have a name for that rigid combo of the crust and the very top of the mantle. They call it the lithosphere. And finally, right at the very center, you get to the core. Just imagine this incredibly dense ball made of iron and nickel. The heat and pressure down there are so intense that it's actually split into two parts. You've got a swirling liquid outer core and a solid inner core. And this is the furnace. It's the ultimate source of all the heat that powers our entire planet.
To really get a sense of the scale here, just look at how thin that crust is. I mean, the crust under the ocean is, on average, just 5 kilometers thick. The continents, more like 30. And yeah, under huge mountain ranges like the Himalayas, it can bulk up to 70 kilometers. But even then, it's just this tiny, fragile shell on top of a massive, super dynamic planet.
Okay, but you might be thinking, how do we actually know any of this? I mean, it's a fair question, right? We've never drilled down to the mantle. Forget about the core. The deepest hole humans have ever dug is only about 12 kilometers deep. So, how'd we figure it all out? Well, the answer is pretty cool. We learned by listening to the planet.
See, every time there's an earthquake, it sends these shock waves, seismic waves, vibrating through the entire planet. It's almost like giving the Earth an ultrasound. Now, there are two main types of these waves. You've got P waves, and they can plow through pretty much anything, solids, liquids, gases. But then you have S waves, and S waves have one really, really important rule. They cannot travel through liquid at all.
And that one little rule led to this brilliant aha moment. Scientists set up detectors all over the world, and they started noticing something weird. S-waves from an earthquake on one side of the planet, well, they just never showed up on the other side. It created this shadow zone. There was only one possible explanation. Those waves must have hit a giant liquid layer that they just couldn't get through. And boom, just like that, by basically listening for what wasn't there, we discovered the liquid outer core. Okay, so now we've got the structure down, but that doesn't explain the movement. What's the engine driving this whole thing? Let's dive into the incredible forces making it all happen.
Seriously, thinking of it like a giant pot on a stove is the perfect way to picture it. All that heat from the core isn't just sitting still. It has to go somewhere, and it creates motion. It's this incredible energy that's been around since the Earth first formed, and it's still cooking.
So here's how it works. That crazy heat from the core warms up the rock at the bottom of the mantle. And just like hot air, that hot rock becomes less dense and it starts to slowly rise. Then, once it gets up near the crust, it starts to cool down, gets denser again, and sinks right back down. This creates these massive, super slow-moving circular currents. They're called convection cells, and that is the engine that is literally dragging the plates on the surface along for the ride.
And get this, that engine in the mantle is so unbelievably powerful that it has completely cracked the lithosphere, that rigid outer layer. So it's not one solid piece at all. It's shattered into about 7 major plates and a whole bunch of smaller ones, almost exactly like a cracked eggshell. And every single one of those pieces is just getting pulled along by those currents down below. You know, this whole idea seems pretty straightforward to us now, but it really wasn't always that way.
It actually took decades of brilliant scientific detective work, with clues coming from all over the place, to finally piece this puzzle together. It really kicked off back in 1912. A guy named Alfred Wegener noticed that the continents looked like they fit together, like a giant jigsaw puzzle, and he proposed this idea of continental drift. The problem? Most people thought he was nuts because he had no idea what could possibly be powerful enough to move them. Fast forward to the 1930s, and Arthur Holmes comes along and suggests, hey, maybe it's convection in the mantle. Then, the final piece of the puzzle fell into place in the 1960s when we discovered seafloor spreading at mid-ocean ridges. That was the smoking gun. And suddenly, all these different ideas clicked together into the grand theory of plate tectonics.
So, remember, these plates are always on the move. And all the real action, all the geological drama, yeah, that happens right at the edges, where these massive slabs of rock run into each other. And there are basically three main ways they can interact. First, you've got divergent boundaries. That's where plates are pulling apart from each other. Magma comes up from below to create new crust. The Mid-Atlantic Ridge is a perfect example. Then you have convergent boundaries, where they're colliding head-on. This is where you see crust get destroyed as one plate dives under another, or where they both crumple up and form gigantic mountain ranges like the Himalayas. And finally, you have transform boundaries. Here, they're just grinding past each other sideways, creating massive fault lines.
So, the key thing to remember here is that these boundaries aren't just lines on a map. They are, without a doubt, the most geologically active places on the entire planet. All that friction, all that pressure, that's what triggers the huge majority of all earthquakes and volcanic eruptions. Okay, let's take a step back and pull all of this together. Let's look at the incredible big picture that this theory gives us. It's really a beautiful, connected story when you think about it. You start with a layered planet with this incredibly hot core. That heat from the core drives these massive convection currents in the mantle. And those currents, in turn, move the rigid tectonic plates floating on top. And finally, it's the way those plates interact at their edges that creates everything. The mountains, the volcanoes, the earthquakes that shape the world as we know it. And really, that's the ultimate takeaway here. Our planet isn't some static dead rock. It's a living, breathing system that is constantly in powerful motion, all driven by this incredible heat and energy from deep, deep inside. And you know what? This process is still happening. Right now, as you're listening to this, the continents are moving. It's slow, about the same speed your fingernails grow, but it's happening. And that leaves us with a really fascinating question to think about. With everything we now know, what will our world actually look like in, say, another 100 million years?